So welcome to the video part 2. I think I got cut off at the end and I'm not 100% sure where, but I think it was on the basic computation part. So you can go ahead and type this into your graphing calculator or your scientific calculator. You will need a scientific calculator for your next test, and you should have ended with 25.1 degrees Celsius. So that is trapezoidal approximations in a nutshell. All right, are you ready? We'll flip the page. Midpoint sums are very similar. I want to try to do this one without creating a graph, mostly because our table here is set up perfectly for that. But in general, when we're talking about a midpoint sum, imagine that you had a function, right, or some sort of graph or some data points. The way that this is going to work out is that you're going to take your interval from here to maybe here, and in previous approximations, we've done a left sum where we've built on the left, or a right sum, or an upper or a lower. With a midpoint sum, you would take your interval, and it'll still have that length. But what you would do is you'd compute the midpoint of your interval. And with your midpoint, you would trace up to your function, or maybe your data points, and you would build straight across. If you think about this in comparison to an upper sum, right? If I had done an upper sum or a left sum in this case, I would have been too big. If I would have done a right sum or a lower sum, I would have been too small. And by using the midpoint, I'm a little too small over here, I'm a little too big over here, but the midpoint sum gives me a better approximation than an upper or a lower or a right or a left. Likewise, we could have done the same thing if we had had a graph, an actual curve here. Trapezoidal will just give you a better sum than perhaps an upper or a lower or a right or a left. Students ask me every year, well, then why do I need to know them? Why wouldn't I just go with something that goes with the better sum? Well, there are 6 kinds of Riemann sums: upper, lower, right, left, midpoint, and trapezoid, and you have to know all 6 of them for your AP test. So the short answer is because there are 6 kinds and you need to know them. But anyways, you should also know about midpoint sums. Here we have a data table instead, and data tables can be a little bit tricky, but this one is designed for a midpoint. It says that we have a test plane that flies in a straight line with a positive velocity v of t. And in our table here, they've given us the velocity of the plane at specific moments in time. So it looks like we're measuring our time in minutes and miles per minute for our velocity. And they've given you just selected values of your velocity for the first 40 minutes. Right? Notice they're counting by 5s. They want you to come up with an approximation for the integral from 0 to 40 of v of t. We'll come back to the meaning of that in just a second, but notice they're telling you again, you want to do a midpoint, you don't get a choice, and they're telling you to just use 4 subintervals. So if you took your 40 unit long interval and divided it into 4 parts, each of those intervals should be 10 minutes. So you'll have an interval from 0 to 10. And then your next interval would be from 10 minutes to 20 minutes. And then your next interval would be from 20 to 30. And then your next interval would be from 30 to 40. If I only had those values, 0, 10, 20, 30, 40, I would not be able to do a midpoint approximation with a data table because you don't know what the midpoints are. So this particular set of data is designed perfectly because it just so happens that the midpoint from 0 to 10 is 5, and I have that data point. The midpoint from 10 to 20 is 15, and I have that data point. The midpoint from 20 to 30, 25, right? And the midpoint from 30 to 40 is at 35. So they've given you data that is perfectly aligned with how this should work. If I want to integrate from 0 to 40 of v of t using this midpoint Riemann sum, then I would look and I would set it up just like we did with upper, lower, right, and left. I'm using rectangles, base times height. So for that first interval from 0 to 10 minutes, I have a 10-minute span. And out of those 3 numbers, I'm going to choose the 9.2. I'm going to determine the value of my function at the midpoint, so 9.2. Then I would add in for the second set of intervals. So from 10 to 20, That's another 10-minute span. So the base of that interval is 10 minutes, or sorry, 10 units. And then I will use the 15, the midpoint value, to determine the height or the value of my velocity function. And I'll keep going like this, right? From 20 to 30, that's another 10-minute base. And I'm using the midpoint at 25, 2.4 miles per minute, to calculate the velocity at that moment. And last but not least, from 30 to 40 is 10 minutes. And I'm using the midpoint at 35 minutes, so 4.3 miles per minute, for the actual velocity that I'm going to use. So you could plot a scatter plot just like we did before. If you're not sure how I came up with these numbers, that would give you a nice idea, but hopefully you guys are starting to see the connection between the data tables and the construction of the computation. This one's really nice to multiply out because you have 92, 70, those 10s just let you sort of move everything over, or you could have factored out the 10. There's lots of ways to do it. You should be getting 229. You want to use correct units and explain your meaning of your approximation. So if you remember something called the net change theorem, every time you're measuring the integral of a rate of change, then you're getting the change in whatever it is you're measuring. Since velocity is a change in the measure of distance, then this is 229 miles, right? It'd be the change in position over the first 40 minutes. Or you could have memorized this. This is just your displacement function, right? So that would also work. The explanation part of this then would be that you would want to make sure that you stated that, let's see, this is a plane. So the plane flies. We want to refer to that value, 229 miles. And you always want to refer on these explanation questions to the boundaries. You want to tell the reader that you understand what the 0 and the 40 stand for. So the plane flies 229 miles in the first 40 minutes of flight. You could phrase that lots of different ways. You could say something like from time equals 0 to time equals 40 minutes. The plane flies 229 miles. There's no one right answer, but you would want to make sure that you refer to the total using the correct units. And you would also want to have addressed the matter of what the 0 and the 40 stand for. So I've left you guys with the Riemann sums practice worksheet for today. It is, if you're watching this in 2019, it is not due tomorrow. You could work the rest of the hour today on studying for your quiz for 4-5 tomorrow. And then you could take this home for the weekend. Answers will be posted on the Schoology site. There's only 5 questions. And actually be careful because number 5 isn't actually asking you to calculate anything. It's asking you to make a comparison. And I know they all have multiple parts, so it might take a little bit and a couple pieces of paper. But work on those for Monday, and that way I can answer questions for you. We're going to review on Monday and prepare for our test on Tuesday. All right. Thank you guys.